All right, so I just want your attention for this part to clear up any problem, and thank you very much for pointing that out. Whenever you have a voltages and if they are in the Y, and I like to put that there, configuration. For instance, if they have something like plus or minus VAN, or at some angle, I'll just call it theta AN. I hope you can see this. If that's a Y voltage, its relationship to a delta voltage would be, and this would be small a, B, this would be A to neutral. VAB here would be equal to the square root of 3 times the magnitude of VAN, and the angle would be that angle, whatever it is, I call it theta AN plus 30 degrees. And in a like manner, the opposite would be true. If you were given a delta voltage, for instance, if you were given VAB at some angle theta AB, and this is the delta configuration over here, VAN would have a magnitude of VAB over the square root of 3 at an angle of theta AB minus 30 degrees. Now I want to be clear about that. That is the relationship between delta voltages and Y voltage. When we talk about loads, and this is where the mistake is, if these are Y loads, and I'll just call it ZY here. To get to a delta load, Z delta would be equal to 3 times ZY. You don't have to worry about phase. It's that simple. Take 3 times it. Y'all with me? Can everybody see this in the back, by the way? Far back. All right? And if you had Z delta, and you wanted ZY, ZY would be simply Z delta over 3. Now in that homework 21, there is a relationship of delta to Y impedances where it says square root. I will correct that. Can you send me an email about that? Just send it to me, I'll correct it as soon as I get there. All right, and I apologize. Did anybody else notice that? Oh. It's not a problem, it's a statement at the top, I guess. Thank you very much. I'm sorry about that. I will correct it as soon as possible. All right. We good on that, class? Now, anytime, and the last time I said, anytime you're doing the problem class of 3-phase circuitry that we're talking about, you always take the delta configuration and turn it into a Y. Then you get the line curves. You all hear me on that? Anything else that's asked for, either the Y volt or delta voltage or delta anything, you get from the Y information. I'm trying to be absolutely clear about that. For instance, if I gave you a source, I'm just trying to be clear about one. Suppose I give you a source voltage that is in a Y configuration. And then I have a line impedance. And I have a load that's in the delta configuration. And I ask you for 2 pieces of information. I asked you for the line current, and I asked you for the voltage across the delta load. You all hear me on this? I'm going to draw this one out, because that way it'll clear up any uncertainty or confusion. I want to do this one. Now, I didn't get a question about this. Well, I did sort of yesterday, but not in the direct sense. I'll take your questions about the homework in 1 second, but I want to take care of this. So, suppose I have this. You ready? Now, usually they're just word problems. I'm not going to draw out all the 3 phases. It just takes too long. But I'm going to draw the simple phase. I'm going to have a Y source voltage, and I'm going to have a delta load. Okay? But I'm going to have a line impedance. And I'm going to say the line impedance is just, I'll call it 1 plus J1. And say the delta load, Z delta, is equal to 15 plus J15. You know why I've chose that already, ohms. And I'm going to say the Y source voltage, VAN is 120 at an angle of 0 degrees, volts RMS. Y'all with me? So now we're going to draw the equivalent YY first. Y'all follow me on this. I want to make sure you hear me loud and clear on this. So we're just doing Y source, Y load. When we do that, we have to account for this. So here it is. Plus to minus this, I'm going to ground that. This is 120 volts RMS at 0 degrees, just VRMS. Now I put the line in there, 1 plus J1. And then here's cap A, that's small a. Now I put the equivalent Y load. That would be the delta load divided by 3. Does everybody follow me on that? I don't want anybody to miss this. With me? By 3. And grounded. This would be capital N. Everybody with me? That is a YY configuration equivalent of the delta load. Y'all with me? To get this current, it is as simple as it looks. That current is the line current, or I small a cap A. It is simply going to be that voltage, 120, forget the 0 degrees, over 6 plus J4, right? Now I'm just showing you the math. Do you all agree with that? It would be this, 1 plus, did I do that wrong? 1 plus 5 is 6, 1 plus 3 is 4.
It's not. It'd be J5, right?
What's it?
It's a 5.
This? Which, oh, I'm sorry. 5 plus J5. My bad. Thank you. So in this case, it's going to be 6 plus J6. My bad. I'm trying to underscore the points. I'm sorry. You're with me on this, class? The current is given by that. And by the way, just looking at this, I think some of you know this. That's going to be 120 over 6, right? Square root of 2, so 120 by 6 times square root of 2 in the bottom. And then what's going to happen is the angle here is going to be plus 45. On top, it'll be minus 45. Don't worry about that if you don't see it. Your calculator will give it to you. Y'all with me, class? Now, if you were asked for only magnitude, VA, B magnitude, y'all follow me? That's the voltage here, that would occur on the load side. Can you all follow me on this one? What you first have to get is this voltage, right here. You got to get plus or minus V capital A-N. And that's going to be basically that current. And I can do it this way. Just take I small a cap A times 5 plus J5. And I really don't care what that is, but you follow me. That's the math. It'll be a magnitude and angle. Everybody with me? All right. Now, can you say it or not? Over here, guys. If you want the magnitude of V cap A, cap B, right here, you would take the square root of 3 times the magnitude of V cap A, cap N. Do you all follow me on that? So it would be the voltage developed across the load, the A, capital N, load, times the square root of 3. Everybody with me? Now the angle would also be advanced by 30 degrees, if that was asked for. Usually I'm interested in the magnitude. But now the angle would be whatever this is, and I might as well just say it's VAN magnitude at some angle theta AN. Now it's going to be theta AN plus 30 degrees. And I don't want to confuse you. I'm just saying those relationships of the square root of 3 hold for voltages on the load side as well as the source side. Everybody got that? Now, I'm not going to ask you about the current that would be VA, or I should say, through the load across capital A, capital B. But if you wanted them, you would simply take this voltage and divide it by Z delta. Do you all hear me? If you wanted the current flowing from point capital A to capital B through that load, the delta load, you would take that voltage, divide it by Z delta. It's that easy. But I don't want to make more of this than I need to. I just want to be absolutely clear about how you do these problems. You got me on that one? Now, one last thing. Give me a second. One last thing. When you get a current through a delta load, that is not the line current. The line current you can only get with a Y equivalent. Remember that. Unless you want to mess around with the square root of 3 and adding 30 degrees to, I really don't want to have too much informational confusion. All right, I'm trying to just get to the bare bones thing that'll make your life simple for any of the quiz or test questions. And in the real world, that's all you need to know. All the rest, yeah, you can talk about it. It doesn't do a bit of difference, make a bit of difference for anything. Yes, sir.
You also talked about finding average power.
Yeah, and I love, why don't we talk directly about finding average power for this example? Got me? Everybody? I want to make sure I see that. So I'm going to erase this stuff and I want to focus on that. I got this question yesterday. So we've got this situation. Let's assume we know the current. With me? So now, what power are we talking about? If we're talking about the power delivered to the load, and it would be the average power. The way I would do it, this is average power, not complex power. The way hopefully you would do it would be to realize the only thing that is the magnitude of IRMS squared times the resistance, R load. So R load there, just the resistive part of R load, or the real part. It would only be 5 times IRMS squared. How many understand that? That's it. Now, people get hung up and say, well, average power is magnitude of VRMS, so I should calculate that times the magnitude of IRMS, so I need to calculate that too, and then times the cosine of theta V minus theta I at the load. A lot of calculations. You don't need to do that. Y'all hear me? You don't need to do that. You got the current, square the magnitude. Don't have 5 plus J5 or something like that and square it. All right, because you're going to get the wrong answer. You have to take the magnitude of that and square it. You all hear me now? There's a lot of stupid mistakes people make, sometimes because they're not listening to what's being said before a quiz. You just take that current and square it, the magnitude times the resistive part. If you wanted the total power, better yet, average power dissipated here, you would take I squared times 1. You follow me? That's it. Don't make it a big deal. And what people will do, and I've seen this, They will calculate all this information when they've got it right before their eyes. That's what I'm saying. Are you with me? Yes?
And I wanna make sure, line curve requires Y. It requires Y.
Everything Y. Just think Y. That's it. Does everybody hear me on this one? You want me to say it again?
The IRMS part for the top, where is that coming from? Like, how do you use that?
How did we get IRMS for that one? You tell me, guys. How did we get the line curve? Anyone? We took that voltage, 120, and we divided it by the total series impedance, which happened to be 6 plus J6. That's all. There's nothing more to this. I mean, sometimes, I'm not sure if you're looking for a trick. There's no tricks. There really aren't. But you do have to listen, because it makes sense if you think about it. It's as easy as that. You got that current, you got the power dissipated. Now somebody's gonna say, what about complex power? I'm not gonna ask about complex power now. But if you wanted complex power, it would be what? Take the actual polar form of VRMS, take the voltage here, that is the current times that load, right? And then you have to conjugate it. You would take the voltage developed there first, then you would take the current and conjugate it, and multiply the two together, and you would get the complex power. Are you with me? I'm not trying to insult you. I'm trying to just be as clear as I possibly can. Sometimes I don't know the best way to do this. All right, now questions. Now I gave you transformer problems. I'm going to do at least one of them, because you need to know this stuff. My goal is to get, I'm not going to do this, the earlier problems in there have something called magnetically coupled circuits. In my personal opinion, if it's of little to no value for you, an electrical engineer or somebody that's designing magnetic type of transfer circuits, you would use magnetic energy to actually couple them and stuff. Yeah, that would be important, but not to the general, not to you guys. So I'm going to, after this, I'm moving on, and in our text, well, I'll tell you this later, but I'm going to be talking about the most important topics, in my opinion, for you to know, not everything. But one thing you are going to get is operational amplifiers. I'm very curious, have you had operational amplifiers in any of your courses? Have you had programmable logic controllers in any of your courses? PLC? All right, well, you probably are going to use operational amplifiers. They might not call them that, but that's what they are. And that's a very important device for everybody to understand. You will be using it. Now, all right. Next thing I'm going to talk about is transformers. And I know because the quiz is not directly involving this, a lot of you won't do these until you're done with this quiz, but I'd appreciate your attention. By the way, what time do you have to be out of the parking lot over by Bearview Stadium? Is it 10 o'clock still? 11 today? Is there any parking lot on campus besides that where you have to be out in the morning? I'm asking. My car, I think, is safe. I got it towed one time. It's awful. They changed the rules with time changes. Anyway, so what I'm going to do, I want to do one problem that I assigned. Does anybody have one that they would prefer me to do? Has anybody done any of the problems of transformers? You have? Do you want me to do a problem? Give me one. They're all about the same. All right, hold on. I'm going to do one of these. Now, I want to do, if you would pay attention, I'd really appreciate this. Some of this stuff is going to probably help you in the long run. You're going to see probably transformers at some point in your careers, either for your own personal sake, dealing with home stuff, or on the job. They're used everywhere for everything. So this is going to be, unless you've got one for me, I'm going to choose problem 820 if that's okay with you. Okay? All right. This is problem 820. And actually, boy, I wish I'm going to add some more information. Here's the problem, but I'm going to say this is V source here. Now, he does not put V source there. It would be an RMS, yes, but he has V source here. Then he has 2 ohms, and he has minus J4. Hey, Varun, would you come down here and start just calling the names of the people's tests so they can pick them up? Just come down here, don't worry about me. And as he calls your name, please come up and get your exam that was regraded. Y'all with me? And try to be quiet. So, got minus J4 here. Then, I got a transformer. Now notice where the dot is. I'm trying to tell you the secrets of doing these things so you don't mess up. The dot is critical. This is the dot. This indicates where V1 is. You need to always label where I1 is. That is the primary side. Now these 2 straight lines indicate it is an iron core transformer. It's a heavy one, and it's for low frequency operation. That's all that means. Then you're going to have another set of coils over here. And you're going to have a dot there, and this will be V2. And this will be the current. Now the current always flows in to the actual terminal it's dotted. I'm going to have to talk over him, but as he calls your name, you can shout it out. Don't worry, you're not going to bother me. I've taught in very loud classes. And they have this. And I have this. And they have this. And they want this. Now this isn't in the problem, but I'm going to put it there. Put this down. Hint, this may be something you see again. I can't be more clear. Not today, but you will see it again. I'm going to make this 100 volts at 0 degrees.
Jared?
With me? RMS. And here's what's wanted. This voltage V out. Now that voltage isn't in the problem, but we're going to do it. We need, every step that I'm going to show you in this problem is important to understand. Can everybody follow me? Here's the first thing that you do. You have to find out what the impedance would be across this transformer looking through the primary side. That's the first step, and it is the critical step. So when I look at this transformer,
Henry?
I want to know what the equivalent Zn is here. That's what I'm looking for.
Hollis?
I have this on the other side. And then the turns ratio on this one is 2 to 1. This is important. So it says for every 2 turns on the primary side, I have 1 turn on the secondary. Label this in your notes. Put an N1 or the number of turns on the primary side there and N2 here. These will always be ratios. So for every 2 turns on the primary, you have 1 turn on the secondary. Everybody with me on that? Now, the next thing you do
trái trứng bóng.
I have 2 to 1. And then the total impedance here is going to be 3 minus J2.
Clear?
Can everybody follow me? Now the equation says this. Z primary is equal to N1 over N2 squared times Z, and I'll call it load, or the secondary. This would be on the side of the primary. This would be on the side of the secondary. Can everybody see that?
Amanda?
Now, I'm going to tell you a way you never, sort of a guide so you don't make mistakes.
Chain?
Oops.
K?
Yeah, that's it. Whatever side has more turns, in this case, this side, has more voltage. You all with me on that? So if the voltage here was 5 volts, the voltage here would be 10 volts. You with me? Whatever side has the least turns has the largest current. And here's what you think. You always, if you want to get anything about this, if you go from a side of a transformer that has less turns than a side with more turns, like this case, the impedance is going to go up by the square of the turns ratio. In other words, this impedance here will be multiplied by 2 squared, or 4. You all hear me? Can everybody hear me back there? With me? Now, if you look this way, and you had an impedance here of, say, 5 ohms, on this side, if you were looking there, it would be 5, but it would be divided by 2 squared of 4. You all with me? So the side with more turns, more voltage. The side with least number of turns or less turns, more current. If you actually ratio, this is what you get. You with me, class? So the very first thing is, I can say that this circuit here on the primary side really looks like this.
You better.
You're going to have, in this case, 100,
Braden?
or just 100 volts RMS. You're going to have 2 minus J4. And now, where the transformer was, we simply put an impedance of 3 minus J2 divided by 4. So this impedance is going to be 3 minus J2 divided by 4. Can everybody see this, by the way, in the far back? Now, at the next thing, this is the key. Once you get this impedance right, the problem falls apart. The next thing you get is this current, I1. And this is the dotted terminal. So this is the equivalent effect of that transformer's primary side with the secondary load. Now that current is found just like you find any other current. You take the total series impedance and divide it into the source voltage. So I can say that I1 would be equal to this, and I'm just going to add them this way. I'm going to say it's going to be 100 volts, or Vs, divided by 2 minus J4 plus quantity 3 minus J2 over 4. I'm leaving it that way so you can see where I got everything. Can everybody see that and understand that? Now, once you have the primary current, the relationship to the secondary current, here's I1, here's I2, it is this. N1 times I1 is N2 times I2. If you write that down and understand it, you will not make mistakes. So we want I2. Does everybody follow me on this? We're going to need I2 because if I have I2, which is flowing this way, I automatically have this voltage right there, don't I? 2 ohms times I2 would be that voltage. Now the polarity is wrong, is it not? So I would put a minus sign in front of it. Y'all with me on this, class? If you are, please let me see your hands to understand. Amanda, do you understand this or not? God, you're looking so. I mean, honestly, do you guys got it? All right, now, I2 here would be what? It would be N2, which is 1, over N1, which is 2, or 1/2. Wait a second. Hold on.
Jack what? Bennett?
No.
Griffin?
So for this one,
Chris Walden? Grant? Fred Peebles? Grant Holmes? George Peter? Josh Robinson?
all right.
Reed James?
Now, I'm just telling you, it'd be a turns ratio business, and what, to get this voltage magnitude, you would take that current multiplied by 2 ohms. We're gonna have to get this quiz out here in a second. How many more do you have to go?
I think just a couple more.
Tell you what, we need to, I'll get the rest as you come up. I'll get you yours, all right? So would you do me a favor? Take everything off your desk. I'm running out of time. I'm sorry. And